Welcome to SanfordFlipMath. We are in PreCalculus, working through the Demana Waits Foley Kennedy book. We are in Chapter 6, Section 5 now. We've been working with polar coordinates for a bit, and we've talked about how to graph individual points. We've talked about converting back and forth for points and for equations. And this next section here, this next lesson, is really going to be about exploring what some of the cooler shapes for polar graphs look like. We'll do just a little bit of conversion back and forth, probably one on this screen, one on the next, and then we'll go from there. So really what I want to do is focus in on using the technology and using a graphing calculator to kind of see what things look like. And so this first equation, r equals 3 secant theta, and we'll do a little bit with transferring graphs from the calculator to a polar graph. 3 secant theta. Well, so I'm going to come over here and type that in. Now the problem is that 3 times secant, well, there's no secant button on my calculator. So just a reminder that secant's really 1 divided by cosine. So I'm going to do 3 divided by cosine, and when I push the X button, it actually looks like theta because we're in polar mode. If you're not in polar mode, just push the mode key, arrow down, and not parametric, but this time polar. And if you don't want to be in polar mode, if you want y equals in your y equals menu, then you can get out of it by selecting function and hitting enter. So I'm going to quit. I'm going to go back to this is what that looks like. Also, mode-wise, I happen to be in degrees, and so my theta min and max are in terms of degrees. I'm going way up to 1440, and this is just 360 times 4. Just because I want to make sure I go around enough times to do the whole graph. Sometimes you're going to want just 360, sometimes you're going to want more or less. Just keep in mind that I think 1440 is going to go high enough to do pretty much everything I want to do. I might have to wait a little bit, but that's all right. 7.5 is my theta step, and really what the thought here is I'm looking for 15 degrees per step, because that gets my multiples of 30 and my multiples of 45. And 7.5 is half of 15. It just gets me a little more smoothness to the curves. And the rest of the numbers are here from a zoom decimal screen. So I'm going to go back to graph, or I'm going to push graph, and look at that. So bizarre enough, this graph looks like just x equals 3. So what's that look like if we were going to graph it on this screen? Well, here's 1, 2, 3. That's how I'm numbering here. And it's just a vertical line. So this is kind of a weird one to graph on a polar screen, but that is what it is. That's what r equals 3 times secant of theta is. Now we have converted something like this in the last video. I'm just going to take a second here and convert this over into rectangular. So this is r equals 3 over cosine, because 1 over secant is the same thing as cosine. Secant is 1 over cosine. I'm going to multiply both sides by cosine. Okay, so I have now r cosine theta equals 3. And if you recall, cosine's like x. So r cosine theta is really just x. This is x equals 3, which really should be no surprise that this graph looks like this then, because that's x equals 3. Okay. Now, what I'd like you to do is think about what do you think this graph is going to look like based on what I see here. Cosecant is a little different. It's r equals 2 cosecant. So just take a second and think about what that is. You even hit pause, maybe try and guess. Graph it in your calculator first. Okay. Okay, so what I'm going to do is go over and do 2 cosecant. So this is really 2, and then I'm going to do sine here. And let's see what this looks like. So does it look like what you think it should have looked like? Based on what your guess was after seeing 3 secant being x equals 3, this is 2 cosecant, and it looks like y equals 2. Okay, so I'm not going to convert that. I'm just going to say this is what it is, and you can go through the process and convert it, but what you should end up with is y equals 2. Okay, all right, let's do some more. Now, so this time it's not 3 secant, it's 3 cosine, and what you end up with is very, very different. Okay, so let's type that in, 3 cosine. Okay, so 3 cosine theta, and I got to delete off that last little extra guy. Okay, so here we go. So 3 cosine. Well, it has a diameter of 3. Okay, a diameter of 3, and then the center is over here on the x-axis. Okay, halfway, shockingly enough. Okay, so just a quick, let me pop back and do a little sketch here. Okay, so it had a diameter of 3, and so that means that the center would have been here, and it looks something like this. Okay, let's just do a quick, now again on the last video in 6.4b, I believe it was, I did a lot of converting. Okay, so, well, I'm going to convert this. I'm going to multiply both sides by r. And so just a reminder that what I'm looking for is r squared, or, oh, these are supposed to have r in them. Okay, I hope I had those right in the last video. That's not good. So this is now r squared equals 3r cosine theta. R squared is x squared plus y squared. R cosine theta is x. And now I'm going to change the form. This is the equation of a circle, and it's in kind of a jacked up form. So, okay, so now completing the square, half of 3 is 1.5, and 1.5 squared is 2.25. X minus 1.5 squared plus y squared. So the center is at 1.5, 0, hey, that looks like that, and a radius of 1.5, hey, look, there's a radius of 1.5. Okay? All right, so that's not a shock. Okay, so this r equals 3 cosine ended up being a circle that had its center on the x-axis, and it had a diameter of 3. Well, let's compare that to r equals 2 sine. So take a second and think, where do you think it is, what do you think it is when it's 2 sine theta? Okay, I'm going to reveal, you ready? Well, holy cows, look at that. It looks like a circle with a diameter of 2, centered halfway between, and it's on, that center's on the y-axis. Okay, interesting. I think you can convert that in your spare time just for kicks. All right, so what we're going to do now is do some playing around with messing with that. So like just a second ago, we did 2 sine of just theta, and so 3 sine of just theta would be, you know, no big shock. Okay, this is going to have a diameter of 3 on the y-axis. Okay, and so that's not a surprise. Now, what I think will be a surprise, though, is what happens when we put a 3 on the inside. Now, just a quick little note. What this does is it changes the period. It means it's going to repeat faster. Instead of going a full 360, it's going to repeat every 120. So that means it should complete kind of a full revolution of a, quote, circle-ish thing every 120 degrees instead of going a full 360 before it goes the full loop. Okay, so I'm thinking it should have 3 circles. I don't know. Let's see what happens. Whoop. Let's go to the calculator. 3 circles. All right, so I'm going to stick a 3 in there inside with the theta. So this will be 3 theta. All right, buckle up. Ooh, this is called a 3-leaf rose. And they're not really circles, but you get the idea. Okay, so kind of get a picture in your head of what's going on here. This looks like a distance of 3. I'm going to tell you that this distance will be about 3, and this distance will be about 3. Okay, and so this is at straight down, so like a 270. This should be these should be 120 apart. Okay. All right. So as we think about that, okay, let's adjust this a little bit. Okay, so here's 3, and I'm just going to kind of sketch. I'm not going to spend my life doing this. Now 120 degrees, which that would be 90 this way, and then another 30. Yep, that's right. Okay, so I should be on this line, and something like that, and then symmetrically over here, and that is what that looks like. Okay. Okay, so let's do another one. Okay, so let's do r equals 3 sine 4 theta. I don't think that this will be obvious. Okay, so we're going to change the 3 to a 4. Okay, here we go. Holy cows, Batman, what is going on? There are a lot of things going on here. That's an 8-leaf rose. Wow. Okay, so this is not an obvious thing. Okay, so quick little note here. Let's just kind of do some of that. Okay, I'm going to go to 5. What do you think is going to happen? There are 5 leaves on this, 5 petals. Okay, let's go to 6. Well, not 56, that would be too many. Let's go to 6 theta, there we go. Alright, a little hard to see what's going on here. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those petals. So when it was 6, there are 12. Okay, so what I'd like to do is come back and just remember when this was just theta, it was just a circle. So let's do this. I'm going to change my window to just up to 360 so I don't have to keep going round and round and I don't have to wait. Okay. Now, I guess you could make the case that this is a 1-petal rose. But what I want to do is I want to trace on here for just a minute. Okay. So think about what's going on. Okay, watch the angles. Okay, they're numbering by 7.5. And as right now I'm at 127 degrees, I'm at 165 degrees, 172.5, 180. And I'm retracing the same exact points again, same locations as I go from 180 to 360. Okay, so it's repeating. Okay. When I change this to 3 theta here, okay, I'm going to trace again. Okay, so I'm in the first quadrant, I'm in that bottom part, I'm in that third part, and notice the angles. I haven't even gotten to 180 yet. Now I'm over 180. So I'm really retracing the same points. Okay, let's do a little comparison. Let's make this 2 theta. Okay, we're not going to spend our life doing that. Look at that 2, we get 4 petals. Okay, so I'm tracing. Now notice by the time I get past 90, I'm actually on a 2nd petal. When I get past 180, I'm a 3rd, and here I am on the 4th. Okay, so when it was even, okay, when B, the number inside, is even, I get 2B petals, or leaves if you prefer. When B is odd, I get B petals. And why again is that? Because they're retraced. Let me just say repeated. I guess that's a better way to say it. Okay. Okay. I just want to do a couple little quick graphs and throw some terminology in, and we'll go from there. Okay. And so I'm going to get rid of that, and let's do 3 divided by the quantity 1 plus sine theta, and just see how that turns out. Okay, shall we? Okay, here we go. Oh, I'm off the screen. What is going on here? Okay, let's do zoom 6 just to kind of cut to the chase here. Well, that is really different. I did not expect that at all. And I don't know exactly what that is. Looks kind of parabola-ish. I don't know. I don't want to spend your life doing this. I just want to zoom out a little bit. Interesting. Looks kind of parabola-ish to me. Okay, that was different. I did not expect that. Okay, let's do this, and this hopefully will be a little more of my liking. Okay, so this is 1 minus cosine of 4 theta. Oh, sorry. Let me go back to zoom 4. Interesting. It looks a little rotated, similar to what we were already doing, but a little rotated. That would still be considered a 4-leaf rose. Okay, let's do 1 minus 2 sine of theta and see what that does for us. Okay, this is called a limicon. It's got a soft C. Limicon. That is a soft C, and it looks kind of like a heart, but it's got a little internal loop in it. Okay. There is something called a cardioid. I think I'm supposed to have another I in there. And a cardioid looks like a heart, and they can be turned sideways. It would be something more like, if I do 2 minus, I think that'll get me that. There it is. Okay, and that does connect down here. Okay, so that's called a cardioid. And if we get rid of the 2, if we make that a 1 and a 1. And really the difference here is because of the way that the ones subtract from each other. There's a smaller version of it. Okay? All right, well, I'm going to leave it at this. And this is where I think things start getting really cool with polar. This is where I get excited. So, I guess we'll leave it at that. And thank you much for watching. This has been polar and exciting stuff. SanfordFlipMath, we're done. Bye.